Hello students, in this video we will study strain energy in shear and torsion. Consider a block of length dx, dy and dz. In this, top face is subjected to a shear stress tau, and because of this tau a force will be acting. The value of force will be shear stress into area, this top face area, which is equal to dx into dz. Because of this shear force, this block will take this form. This top face will reach here, this side will reach here, and it will tilt. This block will tilt like this because this bottom face is fixed. This is the angle it is making, which is shearing strain. Now force acting in this top face is shear stress into area. Now strain energy will be force into displacement. So here displacement is bb dash. So u is equal to half this shear force into bb dash. Half we have taken because we assume that force is gradually applied from 0 to this maximum value. From this right angle triangle you can see that this bb dash divided by AB, bb dash divided by AB is equal to tan gamma for this small angle, which is equal to gamma. So from that you can get bb dash is equal to, now this side is dy, so I have written this side in place of AB, I have written dy. So bb dash is equal to gamma into dy, and put this value of bb dash here, you will get tau dx dz into gamma dy. Now you can simplify this. Dx dz dy is the volume of this block, so volume of block, and tau is shear stress, gamma is shear strain. So u is equal to half shear stress into shear strain into volume of the block. So if you take strain energy per unit volume, you will get small u. So if you divide this term with volume of the block, you will get half shear stress into shear strain. This is the relation. This is the strain energy per unit volume for shear. Now we know that relation between tau and gamma, shear stress is proportional to shear strain. So tau is equal to g into gamma, g is constant, modulus of rigidity. From this relation, if you put value of tau as g gamma here, so value of tau is g gamma, then you will get this value. Or if you put gamma is equal to tau divided by g in place of gamma, if you write tau divided by g, you will get this relation. So these are the different forms of strain energy in shear. In case of torsion, we have torsion formula. T by j is equal to tau by r is equal to g phi by L, where T is the torque applied, J is polar moment of inertia of this cross-sectional area. So here it is circular area. So it's moment of inertia of this circular area with respect to axis, which is perpendicular to this surface. Tau is shear stress at radius r. So if you take any radius r, so at this layer, value of shear stress is tau. G is modulus of rigidity of this material. Phi is angle of twist. This angle of twist is phi. L is length of the bar. From this relation, you can see that phi is equal to TL divided by Gj. You can see that this L, G and J are constant for a particular shaft. That means phi and T are linearly related to each other. So if you plot a curve between this angle of twist and torque, you will get curve like this, a straight line you will get. Strain energy will be work done because of this torque, and we know that work done because of torque is torque into angle of twist. So you will get work done, which is equal to strain energy equal to half T into phi. Again, half we have taken because we assume that this applied torque is gradually increased from 0 to a value of T. So this is the work done. Now in this equation, if you put phi is equal to TL by Gj, you will get this relation, T square L upon Gj. And if you put T is equal to Gj phi divided by L, then you will get this relation. If T is constant, then this equation is good. But if T is varying, then you have to use this relation, integration of Tx square. This is torque at any section x, and this is dx is small length. In place of total length, we take small length, and when we integrate it for entire length, you will get strain energy. Now I am taking tau, that is maximum value of tau, that is tau at outer layer. So that I have taken r, radius as outer radius, the maximum radius. So at this outer layer, shear stress will be maximum. At the center, shear stress would be 0. So this if you take this maximum value of tau, I have not written here tau max, but it is maximum value of tau I have taken here. Now J is polar moment of inertia, which is equal to pi r raised to 4 divided by 2. Now put this value here, that means value of t is equal to tau j by r, put here and simplify. Further put value of j here. So j is equal to pi r raised to 4 divided by 2. So pi r raised to 4 divided by 2, already 2 is here, so it becomes 4. So now this is r raised to 4, here r square, so you can remove this r square. So what you are getting is tau square pi r square L divided by 4g. Now this pi r square is cross sectional area of this circle and L is length. So pi r square L is the volume of this shaft. So you can write this strain energy as tau square divided by 4g into volume of cylinder. Now you can see when we use this tau maximum here, then this relation here we are getting 4, but in previous relation we are getting, in case of shear stress and shear strain, we were getting only tau square by 2g. So here actually we are taking tau max, because tau is varying from 0 to maximum value. That's why you are getting here 4. For hollow cylinder, all these things are same. Only value of polar moment of inertia of this shaft will change. So polar moment of inertia of this shaft will be pi r raised to 4, capital R raised to 4 minus small r raised to 4, where capital R is the outer radius and small r is the inner radius of this hollow cylinder. Now again put this value of t here in this equation and simplify. So again, now this r raised to 4 minus small r raised to 4, a square minus b square, using that formula, a plus b into a minus b, use that formula. So you will get r square plus r square and capital R square minus r square into L. Now in this pi into this term into L is the volume of this hollow cylinder, cross sectional area into length. So you will get tau square divided by 4g, tau square divided by 4g. Now this 3 term I have changed that into volume of cylinder, and what is remaining is capital R square plus small r square divided by capital R square. Now you can see if in this hollow cylinder relation, if you put the small r is equal to 0, so in case of solid cylinder this r will be 0. So automatically we will get the same relation what we have get for solid cylinder. Now we will solve 2 problems. So first problem here, rod AC is made of aluminum and is subjected to a torque T applied at C. So one torque is applied at this point. Now this cylinder, value of this material is, for value of G for this material is given 73 gigapascal, and that portion BC of the rod is hollow. So this BC, this portion is hollow, and AB, this portion is solid. And its inner diameter is given 16 mm. And outer diameter of both solid and hollow cylinders are same, 24 mm. We have to determine the strain energy of the rod for a maximum shear stress of 120 megapascal. Different values given. Maximum value of tau is 120 megapascal. G is given 73 gigapascal. Now length of AB is given. This length of AB is given 400 mm. So I am writing this 0.4 meter. Length of BC 0.5 meter. So this length is given, also given. Now strain energy will be strain energy of this part AB plus strain energy of BC. So you can write UAB plus UBC. Now formula for strain energy is T square LAB upon 2G JAB for AB. Similarly for this part BC. Now here you can see this T is constant for both the sections. So I am writing T in both cases same. Similarly material is same throughout for both the sections. So I am writing G. Both lengths are different, and polar moment of inertia for both parts are different. So I am writing JAB and JBC for polar. Now you can calculate polar moment of inertia for AB solid part, pi by 32 d raised to 4. So I am writing DO outer diameter raised to 4. So outer diameter is 24 mm. So I have converted that into meters. So 0.024 meter raised to 4. Pi is 3.14 divided by 32. You will get 3.25 into 10 raised to minus 8 meter raised to 4. Similarly, polar moment of inertia of BC is pi by 32 outer radius DO raised to 4 minus DI raised to 4 is equal to 3.14. This is outer diameter. This is inner diameter. divided by 32, you will get 2.61 into 10 raised to minus 8 meter raised to 4. Now this tau is given, but we need this value of T, torque, which is not given. This can be calculated from the torsion formula. Tau by R is equal to T by J. That means tau is equal to TR by J. In this value of tau is given 120 megapascal. But this tau is different for this part. That is maximum value of tau. Outer layer of this cylinder and outer layer of this cylinder will have different values of shear stress. Now maximum value you will get in this hollow part. Why? Because you can see that in this relation T and R both constant for this sections BC and AB. For both sections T is constant, T is same. Similarly radius, outer radius is same for both sections. So tau is inversely proportional to J. So tau will be more where J is less. So here in these two cases you can see value of J is less in this hollow cylinder. Therefore tau will be maximum in this hollow cylinder. So we have to take that J which is less. So in that way you can calculate this torque. So torque T is equal to tau J divided by R. So tau I am taking, maximum value of tau is 120 megapascal and J is this one. This value of J I have used because when you take lesser value of J you will get higher value of tau, and divided by R. Radius is same both the cases. So R is half of this 24. So 0.012, that's what I have taken. So in this way you have calculated torque, which is equal to 261 Newton meter. Now you can calculate UAB in this relation. Put this 261 square into length AB is 0.4 divided by 2 into G. Value of G is 73 gigapascal. So 73 into 10 raised to 9 Pascal. 3.25 into 10 raised to minus 8. When you simplify this, you will get this value as 5.74 joules. Similarly, UBC, you will get these two, this is same, 261. Now this length is 0.5, this length is 0.5 meters. Now 273, the same value, this is 2.61. So put this value 2.61, you will get 8.94 joules. So once you get these two values, you can add these two. So in this way 5.74 plus 8.94, you are getting U is equal to 14.68 joule. Now you could have used these two equations also, but I have not used these two equations here because value of tau is different in both the sections. In this section maximum value of tau is different, and this section maximum value of tau is different. Now in this section tau is given for hollow. That means for this equation you don't need to do anything, only use this tau. Directly you can use this tau here. But for this equation you have to calculate this tau. So that way also you can determine this. You can calculate this tau using this relation because tau into J is equal to constant. So tau here into J here is equal to tau at this section into J at this section. By using that relation you can calculate tau at this section. Maximum value of tau at the solid cylinder you can calculate. After that you can apply these two equations and you can determine value of U. So in that way also you can determine strain energy, total strain energy of this bar. So this problem is compare the strain energies of the following two shafts subjected to the same maximum shear stress. Now you can see maximum shear stress tau is same in both the cases. So what are those two cases? One is a hollow shaft having outer diameter n times the inner diameter, and second one is a solid shaft. Masses, lengths and materials of the two shafts are the same. So you can use this relation because tau is same for both the cases. Value of shear stress, maximum shear stress is same. Strain energy of hollow and solid cylinder, ratio of these two you can determine. Now condition for hollow cylinder, for hollow shaft condition is given outer diameter is n times the inner diameter. So for hollow shaft our DO is outer diameter and DI is inner diameter. So outer diameter is equal to n times inner diameter. And other condition is given, masses are same for both hollow and solid shaft. So mass of hollow shaft is volume into density. So volume is cross sectional area into length. Volume is pi by 4 d square. D is the diameter of solid shaft. So pi by 4 d square is cross sectional area of solid shaft into length is volume. So pi by 4 d square L is volume into density I have taken as rho. Now same for mass of this hollow shaft is pi by 4 outside diameter square minus inside diameter square into L into rho. So again same way I have calculated mass of this hollow cylinder. Now here I have taken same rho because both same material, so density will be same, and diameter is different. Pi by 4 is same, length is also given same, lengths of both the shaft are same, so I have taken L and L. So you can cancel out L, rho and pi by 4 you can cancel, so you will get d square is equal to outside diameter of this hollow cylinder minus inside diameter square. So this relation you will get. Again you can take out in place of do square you can write this relation from this, n square di square. So d square is equal to n square minus 1 di square, inner diameter square. And similarly here you need this term r square plus r square divided by r square for hollow cylinder. This is outside radius, inside radius, and this is outside radius. So this is ratio, the same relation you will get for diameters also. This is outside diameter square, inside diameter square, and this is outside diameter square. So when you put these values, you can simplify. Do is n di, so put that value, so you will get n square plus 1 divided by n square. Now here volume of hollow cylinder is equal to volume of solid cylinder. You can see here masses are same, lengths are same, therefore volume of hollow cylinder and volume of solid cylinder will be same. So these two terms are same. So when you take ratio U hollow by U solid, so you can see that shear stress, maximum shear stress in hollow cylinder and solid cylinder both are same. So these two will get cancelled. 4G same material, so G is also same. So 4G will get cancelled. Volume of solid cylinder and volume of hollow cylinder and volume of solid cylinder both are same. So this will also get cancelled. So ratio of U hollow by U solid will be equal to this term only. So this term is r square plus r square divided by r square, n square plus 1 divided by n square, or 1 plus 1 by n square. This is a hollow cylinder, hollow shaft. In this hollow shaft, if this inside radius and outside radius are almost equal, both are almost, that means when this cylinder is very thin cylinder, in that case this both radius will be almost same, so n will be almost equal to 1. Strain energy of hollow cylinder will be twice that of strain energy of solid cylinder. Why? Because when you put value of n is equal to 1 here, then it will become 1 plus 1, 2. For a thick cylinder, when this small r is very small, so n become very large value, so this n square is very large value. So 1 by n square will be neglected. You can neglect this 1 by n square, so it will become almost 1. So in case of thick cylinder, ratio of strain energy of hollow cylinder to solid cylinder will be almost equal to 1. So this value of this ratio varies between 1 to 2. Thank you for watching this video.